Welcome to Lecture 15. This is the second part of the shape selection series of conversations. In the last class, we looked at the fact that depending upon the material shape and material loading condition, the criteria for using an efficient structure, which means minimizing the mass based on a stiffness constraint or a strength constraint for a design, we could arrive at a number of different scenarios that involve creating estimates of the shape efficiency factor. These factors not only took into account the loading and the material and the shape, but they also recognize the fact that certain shapes are just possible for a given material and others are not. And certain shapes are best created by a particular process and others are not. So there are limitations to shapes. Let us continue that conversation, re examining the goals that we had at the outset of how to simultaneously compare different materials and shapes to address a certain design situation that could be based upon a strength limiting constraint or a stiffness limiting constraint. So, accordingly, we are looking at being able to substitute a material while allowing for different shapes in a given design scenario. We had looked into evaluating shape factors based on bending strength considerations, and we indicated that the ratio between the failure strength for a given shape normalized to the failure strength for a standard reference shape, in this case a square cross-sectional beam, would allow us to estimate how much more efficient one of these two geometries based on the circular tube or the I section could be relative to the square cross section of the same area. In this case, the area is b square for the square cross sectional area. So we looked at getting the z moment, and which was sigma y in the denominator and f in the numerator. Right? So the failure strength would be sigma y, the yield strength, times the z moment. For the same material, the shape efficiency factor for bending strength would be z divided by z original, where z original is given for the square shape as a raised to 3 by 2 divided by 6. So if you introduce this term over here in the denominator, you will be able to rearrange terms and say that the shape efficiency factor for any given shape is the z moment divided by area to the power 1.5. Let's take the situation where you have a beam of length L loaded in bending, and it must support a specified bending moment mf without failing and has to be as light as possible. So if you go back to module 1 and 2, you would look into this as minimizing the mass of the beam with a mass of m by L unit length, right, with a mass per unit length of m by L. What material would best satisfy these constraints, and what shape would best satisfy these constraints? So we had looked at the fact that for the strength limited design, the material index of strength raised to 2 by 3 divided by rho would be modified to include the shape factor times the strength, the entire product to the power 2 by 3 divided by rho, right? So this would be a way to include shape factor into the material index so that we could predict the effects of material and shape to find out if it was possible to minimize the mass based on the effective choice of both those variables. Let's look at this bending strength of the beam MF as an arbitrary, in this particular case, an I cross-section beam. If M is the mass, A is the area, L is the length, rho is the density, MF is the bending strength, I is the second moment of area, E is the Young's modulus, Z is the section modulus. The objective is to minimize mass, where M is A times L times rho. For a square cross section, the A would be just B times B, where B is the side length for the square. The constraint here is a bending strength MF should be less than I times sigma by Y, which is Z times sigma star. How do you bring the shape factor into this consideration? The way we do that is knowing that phi is the ratio of the two z's, or 6 times z to the power a raised to 1.5. 6 times z divided by a raised to 1.5. If you resubstitute this z, rearrange terms, you can introduce z as phi f by 6 times a raised to 3 over 2. Now we know that a is m divided by L times rho. So if you eliminate a, you can find an expression for minimal m based on a modified material index. So if you introduce this term over here into this equation and rearrange terms to express everything according to m, you will get an expression which is a product of the functional attribute, the geometry, and material properties, rho and sigma, and the shape factor. So this modified material index that we are looking at, this is a criterion for minimizing R. To minimize the mass, we have to minimize this, or alternatively maximize the reciprocal of this term over here, the material index. So given that now we have a term for the material index and a method to derive it, let's go ahead and look at the situation where we looked at strength versus density plots.